You're back.
Yes, I've moved to a different location.
Are you, so you're shutting down video because of Wi-Fi issues?
Yes, sir.
Cool.
Yesterday was a day in the household, and they're building it down the street, so we were stuck in during a storm with no Wi-Fi, running water.
Did you watch the recording?
I have not yet. We've been moving while we can, working around the rain.
Gotcha.
What did I miss?
We just did some surface integrals.
All right. We doing new stuff today?
Yes.
What are we doing today?
Stuff. It will seem sort of random, but then we will tie it back in tomorrow.
All right.
Hi, Professor Drennan.
What's up, Mary Butler?
Nothing much. How are you doing?
I'm all right. Did you sign up for Math 215 last night?
No. I signed up for Calc 2 actually, but I don't know.
Calc 2?
Yes. Because I told you before I didn't do too well in it.
Okay. So, but you passed.
Yes, I did.
Okay.
But I don't know. I might end up taking both. I don't know. We'll see. Because I'm going to be taking 2 econ classes, and then I was going to take managerial accounting, but it conflicted with one of my econ classes. So.
Hello, everyone. What you eating, Gail?
It's a Filipino dish called adobo.
Mm-hmm.
I think that's the one good thing about being at home is that I just get to eat mom's cooking all the time.
Yeah, that's not bad. That's not bad. My kids do not think that that's the great thing about being at home. They get to eat their dad's cooking. Although we do, I don't know, we do some stuff. Like we got some good avocados and we've been making guacamole most days.
Mean guac can win over someone's heart. I'm not gonna lie.
That's good. All right, shall we get started? I think we might be fairly quick today. I just want to talk about a few things, and then we will tie it all up starting tomorrow. It's going to be great. I promised you cool stuff, and I will deliver, but not today. All right, let's see. What? Hold on. Here we go. There we go. All right. Can you see that? We good? Look at what I got. Look at the only thing I have on my screen today is that thing. Do you know what that thing is? Speaking of cooking, that's a cooking utensil. You ever seen one of those? So you use it. It's I have one, and I meant to bring it to the office, but I forgot. It's not really that useful. I would not recommend buying one unless you are planning to teach multidimensional calculus at some point. But it's supposed to, if you're browning ground beef or ground meat of some sort, it's supposed to like kind of chop it up so it browns easier. Again, I have one. It's not all that great, so I don't recommend it. But I do recommend it as a prop to describe something in multidimensional calculus. So we will come back to that. All right, so let's talk about Green's theorem. Do you remember Green's theorem? Let's use green marker to talk about Green's theorem. Green's theorem says, okay, What in the world does Green's theorem say? It's been a while. It says the integral C of f dr equals the integral of, I think it's df2 dx minus df1 dy dA, and the region is R. And I'll put a plus or minus here because it depends on the orientation, but okay. Somebody who's got some notes handy, tell me if I have Green's theorem correctly stated.
Yes.
Yes? Mary has checked her notes. Was that you, Mary? Who was
Yes,
that?
it is.
Okay, so Mary's checked the notes, and she has confirmed that this is a correct statement of Green's theorem. Okay, so here's what I want to do for reasons that are not clear at the moment, but I want to take this df2 dx minus df1 dy, and I want to just give that a name. So let's call this thing the scalar curl. So we're going to call this the scalar curl of the vector field F. That says scalar curl. Okay, so to be more precise, I will just write this down here. Given a 2D vector field F, and that thing is a function, comma, another function, F1, comma, F2, we'll define the scalar curl of it to be df2 dx minus df1 dy. Define, let's call it SCURL. SCURL of F equals df2 dx minus df1 dy. Okay. Okay, so, and again, this is pronounced SCURL or scalar curl. So this is a term that I have heard used before. Some books will use the term scalar curl. Not very many books will use the term SCURL. I think the term SCURL is useful, if for no other reason than that it allows us to write Green's theorem a little more succinctly. Integral C f dot dr equals integral r of the SCURL of f dA. Okay. So that's Green's theorem. How are we doing so far? Everything going all right? You can see 3 faces. I see no complaints. Gail's happy, Jennifer, Sarah, everyone's happy. All right, so we haven't done anything. We just gave a new term to this df2 dx minus df1 dy. Okay, and so we restated Green's theorem. So now let me sort of put this in context. All right, so let's say this is all in 2-dimensional space. Let's say everything we're talking about here is in 2-dimensional space. All right, so what we have is a function. All right, I'm going to draw a little diagram here. Vector field function. Okay, so we have this operation called gradient that takes a function and gives you back a vector field. So this is grad. Okay, and now we have this operation called SCURL that takes a vector field and gives you back a function. Okay. So let's just do this real quick. So let's say f of xy equals 3x cubed minus 2xy. Then what is the grad of f? Can you do that? How confident are you that you can compute the grad of f? Pretty confident. I hope so. I'm so confident in you that I'm just going to go ahead and write it down here and assume that you're all with me. I'm so confident that you can do this that I'm going to just write something down and expect you to correct me if it's wrong.
Minus 2x.
Ah, yeah, see, my confidence was well placed. My ability to do math, not well placed, but my confidence in your ability to do math, well placed. This look all right? That's us computing a gradient. So all I want to point out here is that this is a function, and then we do the gradient of it, and we have a vector field. So indeed, the thing that we call grad, the gradient operator, takes a function and turns it into a vector field. The thing that we call SCURL takes a vector field and turns it into a function. So let's just do that real quick. So let's say my vector field f is equal to, I don't know, 2x minus y squared, comma, y, okay? What is the SCURL of f? I'm pretty sure you got it. You got it? I think it's minus 2y. Am I right? Sadie's on board. Mary's on board. Gail's on board. All right. So again, all I'm trying to do here is show you that you know how to compute SCURLs. There's nothing funny about it. If I give you a vector field, you do the SCURL of it, and that turns it into a function. All right. So the thing that you plug into the SCURL operator is a vector field, and the thing that you get out of the SCURL operator is a function. Okay. So let's look now at, so let me just redraw my picture. We have function, vector field, function, and we have the gradient operator does this, and the SCURL operator does that. Now, all right, let's say you're walking down the street and somebody hands you this line integral and says, do this line integral. Okay. My claim is that we have three possible ways that we have three methods of doing line integrals. Who is going to tell me what the three methods of doing line integrals are?
The definition, the fundamental theorem of calculus for line integrals, and Green's theorem.
Love it. That's perfect. Three ways to do it. Good job, Mary. The definition. So that's where you just parameterize the curve, plug stuff in, do that dot product, turn it into an integral. That's the first way we learned. The second way we learned is the Fatokfli, the fundamental theorem of calculus for line integrals. And when you do the Fatokfli, what you're doing is you're finding an anti-gradient and plugging in the endpoints into the anti-gradient, okay? And the third way is Green's theorem. So what I want to point out here is that if you're doing a line integral, then you're dealing with a vector field, okay? And the two ways that we have to do line integrals, the two theorems that we have about line integrals, are theorems that push us either in that direction back towards the function or in that direction towards the function, right? So the Fatokfli says find an anti-gradient and then deal with that function that's the anti-gradient. So if you're given this and you use the Fatokfli, you're going backwards along this gradient line to get to a function that you use to compute the integral. If you're using Green's theorem, you're going in the opposite direction, right? Green's theorem says do the SCURL and then trade in that line integral for a two variable function integral. Okay, so 3 ways to do a line integral. Number 1 is just do it. Number 1 is move backwards along this curve, and that's the Fatokfli, and then moving forward along this curve is Green's theorem. Okay. Am I making any sense at all so far? This is all stuff that you know. It's just kind of looking at it from a different angle. Because what we're going to do now is we are going to do this in 3-dimensional space. And that introduces a whole host of complications. So I'm going to share my screen, and there's my screen. So here's what the diagram looks like in 3 dimensions. We have function, vector field, and function. Okay. And so this is going to be gradient still. This is going to be some new thing. And this is going to be some new thing. So this is our mission for today, is to learn what that thing is and what that thing is. So we are going to define an operator that takes a vector field and turns it into a different vector field. Then we're going to define another operator that takes a vector field and turns it into a function. Okay. So, and these are 3 variable vector fields. So we got X, Y, Z slots. So let's first look at this piece right here. So this operator right here is going to be called the divergence. Okay, and I'm going to tell you how it works. Given a vector field F, which is F1, comma F2, comma F3, we define div of F, that's pronounced divergence of F. And its definition is this simple thing right here. F1, let's say df1 dx plus df2 dy plus df3 dz. Shall we do an example? I'll give you a vector field, you compute the divergence. So F equals, I don't know, x squared plus y squared, comma, x minus y plus z squared, comma, cosine of x plus e to the z. Okay, so there's my F. You are now going to take a minute and compute the divergence of F. What's going on at your house there, Mary? Looks like some commotion.
There's just a lot of people walking around and talking right now.
How's my guy Tazwell doing? He all right?
He's back here doing some work too.
Okay.
He's doing great.
Do y'all have the divergence computed?
2x minus 1 e to the z.
Plus e to the z? How's that look? Yep. Okay. On a scale of easy to hard, how do you feel about computing divergences?
Easy.
Yeah, we like this. This is good stuff. Nothing too complicated about that. We just do a quick partial derivative with respect to x, partial derivative with respect to y, with respect to z, add them up. That's all there is to it. So let me just remind you of what the divergence is. It is an operator that eats vector fields and spits out functions. Okay, and let's just confirm that that's what we did. I gave you a vector field. You ate up that vector field and spit out this object, which is a function. Okay, so divergence takes a vector field, does the divergence of that vector field, and the result of that is a function. Okay. All right. So one thing that you might want to know is, what does the divergence mean? And this is one of these things that if we were sitting in Woods 121, I would have a worksheet that would step us through, and we would sort of come to terms with why what I'm about to tell you is true. But because we're living in the times we are, I'm just going to tell you what the divergence means. And then maybe we'll look at some Mathematica and see if we believe it. So, okay. So a vector field, so this vector field right here, yeah, let's look at this. This vector field right here is a sea of arrows. Okay, so we imagine that we are in a giant aquarium and we see arrows telling us the velocity of the water at each point in the vector field. Okay, now it is certainly possible that at some places in that vector field, I'm gonna shut down my screen so we can all look at my face. There. Okay. At some places in that vector field, it's possible that there's a whole bunch of water like compressing down on that point. At other places in that vector field, it's possible that the water is spreading away from that point. This is what the divergence measures, okay? If the divergence is positive, what that means is that the place where you are is what's called a source. It means there's more water coming away from that point than there is coming to that point. If the divergence is negative, it means that water is sort of being sucked up at that point more so than it's leaving that point. Okay, so the divergence tells you, the divergence at a particular point tells you whether the vector field has arrows that are collecting there or whether it has arrows that are leaving there. Okay, so let's take a look at a couple of examples. So like a real simple one, I'm gonna share my screen again real quick. Can I figure out how to do that? Yes. Okay, so let's take a real simple vector field like 0, 0, negative 9.8. What's the divergence of that vector field?
0.
0, because it's the derivative of 0 with respect to x, that's 0, plus the derivative of 0 with respect to y, that's 0, plus the derivative of negative 9.8 with respect to z, that's 0. So the divergence is 0. Okay, if the divergence is 0, that is what's called an incompressible vector field. what that means is that wherever you are in that vector field, if you're a tiny little speck, there is not water coming out of that speck or water coming into that speck. It's just sort of moving through that speck. Okay. Now, what does the vector field 0, 0, negative 9.8 look like? If I have to picture the sea of arrows that is this vector field,
Is it going down?
Yeah.
Like 9.8?
Yeah, so I have these vectors that are 9.8 units long that are pointing straight down everywhere, right? And so let me get some Mathematica happening here. I don't know if this is going to show up well, but let's just give it a try. So if I am vector plot 3D, wait, you can't see that. Let's do this. Mathematica, yeah. Okay, so I'm going to do a vector plot 3D. My vector field is, I'll just say 0, 0, 1, negative 1. X going from negative 1 to 1, Y going from negative 1 to 1, Z going from negative 1 to 1. Okay. All right. So yeah, this vector field is not very interesting. All it is just a bunch of arrows pointing straight down. Okay. So there's no place here on this vector field where, so imagine you're a tiny little marble in there, except you're made out of a mesh screen so that that water can flow through you. At no point in that vector field is there more water coming in on the top than there is leaving on the bottom. There's the same amount of water coming in here as leaving here. Therefore, you have a 0 divergence. Okay. Just to make this easier, I'm going to cut out the Z. So let's look at the vector field. So I'll just keep this a 2-dimensional vector field. A little bit. Okay. So let's look at a vector field. Let's do a vector plot. X, Y. X minus 2, 2. Y minus 2, 2. Okay, so I'm not gonna write this down. Imagine you have the vector field X, comma, Y, comma, 0. What's the divergence of that?
1 plus 1 plus 1.
Yeah, you should have stopped right. 1 plus 1 plus 0, right? 2. Is that all right? Divergence is 2. That's positive. Okay. So what that means is that, all right, I want to do my vector scaling automatic. Let's try that. All right. So the vector field X, comma, Y, comma, 0 looks like this right here. Okay. So can I annotate this? Let's see. Yeah. All right. So imagine that I'm a little ball right here. Okay. There's a certain amount of arrows pointing into me here, and there's a certain amount of arrows leaving me here. Okay. Now, the arrows pointing into me are shorter than the arrows leaving me. These arrows are longer than these arrows. So there's actually more water leaving that little marble than there is coming into that little marble. More water leaving out of there than coming into there means we have a positive divergence. All right. Sometimes I sort of struggle with how much I should talk about this. I suspect that, Minju, have you ever heard of the divergence from your physics time?
Yeah.
What do you, under what, in what context do you talk about divergence?
In electricity and magnetism.
Okay, so is my discussion here, does that sort of match the idea in your head about divergence?
Sorry, I was kind of zoned out.
Okay. All right. So in a math class, I sort of struggle with how much I want to talk about these sorts of things because from a mathematical standpoint, it's not actually all that essential that we understand it. Okay. So if you're looking at the divergence of an electrical field, then that measures the amount to which electricity is flowing out of a certain point or into a certain point.
Oh yeah, right-hand rule.
What do you mean by that?
Isn't right-hand rule? Is it divergence?
I'm not sure what you're talking about. All right, we'll circle back to that. All right, point is, we are mathematicians, right? We now have this operator called the divergence, give it a vector field, it turns it into a function, end of discussion. Good? All right, and we know how to do it. It's super easy to compute. As mathematicians, we love it. You just do some partial derivatives, you add them up, done. Okay. All right, let's get back on the old screen here. All right, so let's go back up to this diagram here. So the divergence, we just talked about that. It takes a vector field and gives you back a function. We know what the gradient does. It takes a function and gives you a vector field. So that works in three-dimensional space just fine. What we're now going to talk about is this middle part. We need an operator that eats a vector field and spits out a vector field. And that thing is going to be called the curl, not the scalar curl or the SCURL, but just the curl. Okay, and I am going to compute some, I'm going to show you how to compute some curls. All right, so given f equals f1, f2, f3, we define curl of f equals, okay. This is a little complicated. So I'm not going to write the formula. What I'm going to do is write the way that we always think about the curl. Okay, so I'm going to put a little quotation marks around my equal sign because what I'm about to write doesn't make any mathematical sense, but I'm going to explain it. So that is weird. But I'm going to explain what this means right down here. Ready for me? Okay. All right. So IJK, so this is a lot like the cross product, right? The IJK is up there to denote that I'm going to do a little determinant here and put that in the I spot, and then a determinant, put it in the J spot, and a determinant to put in the K spot. Okay. So in the I spot, I'm going to do this determinant right here. What does that mean? That means I'm going, so this is not multiplication because multiplication doesn't really make any sense. This means I'm going to do the derivative with respect to y of f3 minus the derivative with respect to z of f2. So this is df3 dy minus df2 dz. That's what's in the first slot because that's what goes with the I. Does that make sense? Okay, let's do the J part. Now the J part, remember, needs a minus. So I'm just, you know what, I'm just going to put the minus there so I don't forget about it. So there's the minus that comes from the fact that it's the middle part. And then I'm doing derivative with respect to x of f3. So that's df3 dx minus df1 dz. Then in the K spot, I've got df2 dx minus df1 dy. Hey, that's our old buddy the SCURL, isn't it? So the curl really is just the SCURL sort of souped up to account for the fact that there's three things and you sort of are doing all combinations of them. How would you like to do a curl? Gail, how would you like to do a curl? All right, good. Glad to hear it. Like, really, what else are you going to be doing? What better offers do you have right now than computing a curl? None. That's what. Okay, so let's say my vector field is, all right, I don't know, x, y squared plus z, zy cubed, comma, I don't know, x, z. Okay, so there's my f. Y'all are going to compute the curl of f, and I will give you a couple minutes to do it. All right, if you're still working, you can keep working. I'm just going to compute it over here on the side, and then we can compare answers. Did I get it right? Sarah, you doing a curl down there?
Yes.
You getting the same thing I'm getting?
Yes.
Emmanuel, how's your curl looking? Jennifer? Cool. Mary, you good? Sadie? Failing?
All good.
Minju? That's all of us then. Okay, good. We're all in agreement on the curl. All right, so what the heck is a curl? Well, just as a reminder, from a mathematical standpoint, the curl is an operator. Look at the red circle up there. The curl is an operator. It takes a vector field and mashes it all up and gives you another vector field, right? And so that's exactly what we did here. If I can find it, I gave you a vector field, this F, and you computed the curl of F. Oh, the curl of F, which is a new vector field. Okay, so what is the curl? I think after my less than spectacular description of the divergence, I'm not going to say much about the curl. You can feel free to ignore what I'm going to say if you want to, but in case you're interested as to what the curl is, let's look at our meat browner. Wait, you can't see the meat browner. I forgot to share the screen with you again. All right. There's our meat browner. Remember this thing? Okay. So I want you to imagine that my pen here is that meat browner. So I got a pen and it has that little paddle wheel thing down here. Okay. So my vector field, my F, my vector field that I started with is a sea of arrows. Okay. The vector field curl of F, so at any point, curl of F is a vector. And that vector will be angled in such a way that that paddle wheel is rotating the maximum amount. Okay. So if like all the arrows from the vector field are pointing this way, then my paddle wheel is not rotating, right? So if I angled the vector this way, then that might make my paddle wheel rotate because the arrows would be hitting the paddle wheel. Okay, so the curl of F is a vector that will align in such a way that the vectors from the vector field are curling around the vector named curl of F. Hold on. Sneezing.
Does that mean that curl is sort of like the vector that's always there, the vector perpendicular to the whole field at that point?
I'm not sure that makes any sense. It's the perpendicular to the whole. Yeah, I mean, I suppose that makes a little bit of sense. Yeah, because it's angled in such a way that the field is rotating around it. Yeah, I think that makes some sense. So it measures the strength and orientation of whatever little whirlpool type things exist in the vector field. Okay, I don't think I want to say much more about it than that. It's kind of hard to wrap your head around and not essential for us as mathematicians to work with what we need to work with. But the curl of F measures how many whirlpools are in there, what angle they're angled at, and how strong they are. Okay. I think we might be done. All I wanted to do was talk about divergence and curl. So let me ask you this. I'm going to ask you a couple of questions. If I were to give you a vector field and ask you to compute the divergence of it, could you do it? Are you super confident? Any vector field, no matter how ugly. As long as you can do the derivatives or call your Calc 1 friends or your Calc 2 friends or whatever to do derivatives for you, good to go. Do you think if I gave you a vector field, you could compute the curl of that vector field? Jennifer could do it. Mary, could you do it?
I can do it. I just feel like I don't understand what I would be doing. Like,
Okay,
why?
so well, let's just leave that hanging there as motivation, because what we're going to do now. Well, okay. Do you want to preview of why we care about the curl and the divergence?
Sure.
Let's do that, because that I can tell you. All right. So I'm going to take you back to to two-dimensional vector fields. So we have function, vector field, function. We have gradient, and we have SCURL. Okay. Now, if you are doing a line integral, a two-dimensional line integral, then you're living kind of in this world right here, right? You have a vector field in 2 dimensions. And what we learned is that if you don't want to use a definition, you can either use the photography. So what the photography does is it says, don't work with the vector field, go backwards and find an anti-gradient and work with the anti-gradient instead. Okay, that makes your life easier in a lot of cases. Or you can use Green's theorem to, instead of pushing that thing backwards to an anti-gradient, you can push it forward by doing the SCURL. And it says, Green's theorem says, don't work with the vector field, work with the SCURL of the vector field over here. Photocracy says, don't work with the vector field, work with the anti-gradient of the vector field here. Okay, so that's everything we know about line integrals. That's everything there is to know about line integrals. So now in 3 dimensions, here's what we have. We have function, vector field, function. This is divergence. This is curl. This is grad. Okay. These are line integrals. These are surface integrals. Okay. So let's say you have a surface integral. Okay. Right now, the only way that we know how to do surface integrals is with the definition. Right? Somebody gives you a surface integral, we have to do what we did yesterday, which is parameterize the surface, find the normal vector, dot product, double integral, all that stuff. Sometimes it's pretty messy. Okay. So there are 2 big theorems that we can use to make surface integrals easier. Number 1, there's a thing called the divergence theorem that says, don't work with this vector field, work with the divergence of that vector field and do a triple integral over here instead of a surface integral here. There's another thing called Stokes' theorem that says, don't work with that vector field there, push it back here via an anti-curl, right? So go back along this curl arrow and work instead with this vector field and do a line integral here. Okay, so if you're given up here 3 ways to do a vector field, or 3 ways to do a line integral, you either leave it here and do it, you push it over here and do Green's theorem on it, or you push it backwards here and do the photocracy on it. Okay, so we're going to come up with a parallel collection of theorems over here on surface integrals. If you have a surface integral, you just leave it here and do it. That's one option. That's the only one we know right now. Or we can push it forward with the divergence and do a triple integral, or we can push it backwards with Stokes and do a line integral over here instead of a surface integral here. Okay. Likewise, here, if you're given a line integral in 3 dimensions, you can either push it backwards, do an anti-gradient, that's the photocracy, same thing, or you can travel backwards along this line using Stokes' theorem. So Stokes' theorem is going to allow you to convert between a surface integral and a line integral. You got a surface integral and you don't like it, use Stokes' theorem to turn it into a line integral. You got a line integral, you don't like it, use Stokes' theorem to push it forward to a surface integral. You got a surface integral you don't like, use the divergence theorem to push it forward to a triple integral. So all these theorems that we have allow you to convert certain kinds of integrals into other kinds of integrals. And it's a matter of figuring out what the most convenient approach is for for any line integral or surface integral that you happen to be handed. Surely you loved that discussion, Gail. That helped.
Just a little bit. Like it's nice to see that all the things that we've learned so far.
Yes. Yes. And again, I want to point out that, well, we'll point this out later, but when you're doing a surface integral, you're doing almost everything that we've talked about this semester. You're doing, or when you're computing the curl or the divergence or doing line integrals, you're doing almost everything, because you got to do partial derivatives, you got to parameterize surface, you got to do, a lot of times you got to do double integrals, you got to do cross products, you got to do dot products. It's all folded into one neat thing. Yeah. Okay. So, who's happy? We know Gail's moderately happy. Can we consider our business to be concluded for the day? Okay, I think we will do that. So you have some homework in your homework folder that I think you will find to be quite manageable. Just doing some curls and some divergences.
See you tomorrow, Dr. Dren.
Tomorrow, yes, 10 a.m.
I'm
Central Time. See y'all then.